Kristen.
Hey, Professor Griffin, how are you?
Hey. Hello, hello.
Hello. So what cycle are we working on today? What kind of cycle?
It's a diesel cycle. I wanted you guys to work on it. I thought we'd go through it in minute
Oh,
detail.
okay, yeah, I did that one. Okay.
Yeah, I think
Um,
we should go through it in minute detail. Make sure.
okay. Are there any other cycles we're going to be covering?
Yeah, Stirling cycle.
The Stirling cycle, okay.
Yeah, but
I'm not missing anything for this class, am I?
I don't know. Let me look and see. You do a real good job on all of your work. And it says here, Kristen, you're not missing anything.
Okay, good.
You're
All
doing
right, I didn't think I should be. I mean, like I turn my stuff in.
Yeah, you do.
I need all the help I can get. So.
Right. Well,
Okay.
there is a glare on the board, but we're just going to have to live with it. I don't know what else to do.
Okay.
But let's see who else is logging in here. We'll go to participants. Hey, there's Kerman. Kristen and Kerman are with us. Yay. And let's see what time it is. Oh, we got 5 minutes. We can relax. Kerman, Kristen, any questions?
I don't think so.
Okay, we're gonna go.
I didn't look to see what you like. What my grade was on the diesel cycle. I did, but I think I did it okay.
I think I graded it. Did I put a grade on your thing?
I haven't looked, sir.
I bet I did.
I'm sure you did. I just haven't looked yet.
I'm getting caught up, believe it or not.
Well, that's good.
Yeah. Hey, there's Levi. We have another customer. Yay, Levi.
Hello, Mr. Griffin.
Hey, hello. I haven't been outside today. What? Hey, I think the radio said storms this afternoon.
Yeah, I think. Well, at least for here in Muskogee, it's supposed to start about 6 o'clock tonight.
Oh, boom booms.
Yeah.
No, that's all we need.
Yeah.
I just went to the bathroom and the toilet darn near overflowed. That's always fun.
Oh, yeah. That's always exciting.
Fortunately, I have a shutoff that I installed about a decade ago that I can stop any more water from coming in.
Oh, well, that's good.
That's worth its weight in gold.
Yes, sir.
Well, let's see. We just have a few of us, and we have 4 minutes.
Are we just going to count to like 400 points, or are we still going to 500?
Oh, that's a good question. I hadn't even thought of that. Is that Levi or is that Kerman?
Kerman.
Kerman. I guess we're going to have 400 points, aren't we, Kerman? Because we have two exams and a final. Well, no, wait a minute. And a homework and quiz, yeah. Yeah, you're right. There'll be 400 points. Hadn't thought of that.
And is still the final going to take care if you do
I
good on
think the final could replace a lower score. What do you think?
Hey, that sounds good to me.
Sounds good to me. Well, we still have 3 minutes before we launch here. Hey, there's Coy. Coy is on board. Good deal. Well, we'll see if Coy gets a thank you point today. He usually does. He helps us out. You know that? somebody helped me out in my last class. I forget who it was, but I appreciate it.
It was Eric.
Oh yeah, it was Eric. Yeah, Eric was really on the ball today.
Yes, he was.
And there's Daniel. Daniel's with us. We've got a good crowd. Okay, we're going to do problem 74. I forget which chapter we're in. Let me dig this out here. Now, hopefully you've already done this, so you're going to be bored because you've already understood it all perfectly. But just in case, I thought we'd go through it. Let's see if I can get up without knocking everything down. Yeah, we're going to do 1074. And I've got almost 1 o'clock, so we'll get started here. Diesel engine has a state before compression of 95 kilopascals. Well, you see, that's what this state 1 is. State 1 is 95 kilopascals and 290 K. Let me get a red pencil here, and we'll put a 290 K isotherm. Now, the way it works is this would be our 290 isotherm. $290K. I wonder if that shows up. Yeah, kind of. See, adiabats are steeper than isotherm. This here's an adiabat. This one here's an adiabat. It's got a diesel cycle's got 2 adiabats, an isocore, and an isobar. That's what a diesel cycle is. And so we now know that state 1 has 95 kilopascals and 290 K. So we're going to use PV equals RT. P1 V1 equals RT1. And we're going to get the specific volume. Well, here goes. And double check me. Well, you've already done this, so you're going to double check me. So you go 87 times 290 divided by 95. Did you get 0.8761? 0.8761. Yay! We're off and running. Okay, now let me read this and see what else we're going to do here. We are doing problem 1074. It is in my book on page P97. You probably don't have a paper book. You probably have a electronic book, but never mind. It says it has a peak pressure of 6,000 kilopascals. Well, that's this here. See, this pressure here is 6,000 kilopascal. And that's true at 2 and 3, because 2 and 3 are isobars. So state 2 is 6,000. And state 3 is 6,000 kilopascals. Okay, good. Let me keep reading. And maximum temperature of 2400 K. So let me put that on there. That's this business here. See, here's your state 3 temperature. And it is 2400 K. Okay, great. So we know that it's, hey, look at here, it's state 3. This is 2400 K. So look at here, we can go P3 V3 equals RT3. Pretty routine and boring. You guys should be very with me on all that. But let me see if I can get this right. Here goes. 2400, 6,000. Well, I got an answer for the V. It's 0.1148. Now that's the specific volume at state 3. Okay. I don't see what else to do here. Hey, now wait a minute. Uga, I see something. Look here. 1 and 4, this is supposed to be an isochore. It goes straight down. 1 and 4 have the same specific volume. So I can put a 0.8761 right in here. 8761. There we go. We're making progress. Anybody have a problem or a question so far? So far, you're okay. I wonder if you can read all that. Hope so. Hey, let's see who else we got here. Jackson showed up and Don. Good deal. Well, let me keep reading. We are doing problem 1074. It's a diesel cycle. I asked you guys to do it, so you've already done this. You should be bored out of your gourd watching me do this because you've already done it. But just in case, maybe we could go through it. All right, let me keep reading here. Maximum temperature, find the volume, blah, blah, cut off, blah, blah, blah. Man, that's all they gave us. We don't know anything else. Okay, well, let me just put the book down. That book isn't going to help me now. That's all we know. Okay, well, let's look at the adiabat going from 1 to 2. Now, the way that works is if you have an adiabat going from 1 to 2, you can use this equation here. Now let's see what we know and what we don't know. We know T1. See, we know T1. It's 290. But we don't know T2. But looky here. We know P1 and P2. Look here. We know that. And we know this K business for air. We're dealing with air here. K is 1.4 for air. What it is, it's the called the specific heat ratio. It's the ratio of C sub P to C sub V. And C sub P, remember, is 1004, and C sub V is 0.717. Just so you'll be a believer, put that in your calculator and see if you get 1.4. I'm going to try it. Here goes. 1.004 divided by 0.717. Boy, Jove, You get 1.4. It's got a name. It's called the specific heat ratio. The name of this is the specific heat ratio. Specific heat ratio. Okay. Well, look, if you know all this stuff, do we know V1? Yeah. Hey, look at here. We know V1, and of course we know the K. And we don't have V2, but hey, look at here. We could get V2 and we could get T2 from this, couldn't we? Yes, we could, Mr. Griffin. Okay, well, here, let's do it. I think I'm going to go ahead and do it. And I'll bore you some more here. Boredom is good in this class. So T2 is divided by T1, which is 290, equals P2, which is 6,000, divided by P1, which is 95, to the 1.4 minus 1. Well, that's 0.4 divided by 1.4. I'm going to do this on my calculator and see what I get. Here goes. Now you try it too, and we'll see how we do here. Oh, I don't like it when the computer goes bling bling, but I think everything's okay.
That was my fault. Sorry about that.
Oh, it kind of makes me nervous.
Yeah, I was turning on the audio and it, for some reason, decided to beep at me.
I think everything's okay. Now, I did all that, and I got a T2 equal to 9, let's round it off, 948 K. Wonder if that's right. Is that what you guys get?
Yeah, I got
Yes,
that.
I'm gonna put it right here. 948 K. 948 K. There we go. Hey, now look at here. We could go P2 V2 is equal to RT2, couldn't we? P2 V2 is equal to RT2. It sure is. All right. Well, I'm going to do that and get this little V2. Here goes. I'm doing it now. Okay. P2 is 6,000. Well, I got an answer. I'm getting 0.0453. Anybody getting that?
I got something very close to it,
What'd you get?
which I'd have to look through to see which method I used. I got 0.0461.
Okay. Well, now I could have done it this way here. You know what? I could have done it that way, but I did it this way. Just the ideal gas law.
I mean, it's 5 thousandths, so I mean that's extremely close. Or no, wait, 80 thousandths.
Let me see what I got. Did it before.
I'm sure I probably rounded something that made my number come off slightly off or
Maybe
something.
you
But
did.
it's
I
so
got
close.
0.0453. No, I think I'm pretty happy with that.
I agree.
Okay. Now what? Well, what about state 4? We don't know the pressure. I'll tell you what, let's do though. Hey, do you see this adiabat going from 3 to 4? See, a diesel cycle has 2 adiabats. There they are. Hey, you know what? We could go ahead and put in zeros for 1 to 2 because it's an adiabat. And 3 to 4. Those are adiabats. So put those zeros in there. They're adiabats. There's no heat transfer on adiabats. But here's my thinking. Now I'm going to have to make some room here to write this. But we're going to do the same equation, but we're going to go from 3 to 4. All right, here goes. We're going to go from 3 to 4. T4, that's the final. T3, that's the initial when you go from 3 to 4, is equal to P4 over P3, K minus 1 over K is equal to V3. These switch. I don't know if you've ever noticed. You got 4 over 3, 4 over 3, but this is 3 over 4. Now, I showed you guys this, and it's all based on, this equation is all based on this equation here when you have an isentropic process. We talked about this equation. This is an important equation. You got to be careful, though. It's only good for ideal gases. It's only good for, well, this part here is only good if it's a isentrope. But the whole idea of the equation is we're dealing with ideal gases. If you have an ideal gas isentrope, that's 0. And you can take this equation and do some algebra and come up with that equation. I think I did that one day, but it's been a while. That's where it came from, in case you forgot. Okay, we're going to get T4 now, I think. Let me write the numbers and we'll try it. Here goes. T4 over T3, 2400, equals, well, we don't have P4, but I tell you what, we have both of these. V3 is 0.1148 and V4 is 0.8761. And that's just going to be to the 0.4 power, isn't it? Oh, yes, it is, Mr. Griffin. Hey, we can solve that. I'm going to do that. Here goes. Push the wrong button. Starting over. Okay, I got an answer. I'm getting T4 is 1064 Kelvin. 1064 Kelvin, okay. 1064 Kelvin. Let's put an isotherm through there. This is the 1064 Kelvin isotherm. And we have our temperature now at 1064 Kelvin. Hey, now we can get P4 because P4V4 is equal to RT4. And look at here, we know V4 and we know T4. We can get P4. Yeah. All right. I'm going to put these numbers in and I'm going to get P4 now. Can you read Can you read that? It's kind of in the glare there.
No,
Can't
it's
help,
still clear.
but you can still read it.
At least on my screen. Yes, sir.
Good, excellent. Okay, well, here goes. T4, we know it's 1064. And then we're going to divide by V4, which is 0.8761. Well, I got an answer. I'm getting a P4 is 348.6. 348.6.
Yes, sir.
That goes right here. 348.6. We're doing great. And now we're going to finish this and get the rest of it and answer their questions that they wanted us to do. But before we do, anyone have a problem with any of that so far?
No, sir.
Okay, good deal.
Just making sure. So I should go to 4 digits, right? Because I think I went to 3, and I got 348.79. So
Well, that's
I
okay.
might hold it off because I got.
I'm not gonna fuss with you on that.
Oh, okay.
One of us might have rounded off something. Okay, well, let's. I need the room now, so I'm going to erase all this, and I'm going to calculate these delta little u's here. Oh. All right. Now, this is a piston cylinder thing. So delta U is equal to Q minus W. It's a control mass. It's a piston cylinder. We're treating it as a control mass, even though we're lying to you because you do have exhaust and intake. But see, I tried to explain to you the exhaust and intake are modeled by this isochoric process from 4 to 1. And the thermodynamic cycle is considered a control mass. Okay, well, let's do delta U from 1 to 2. Well, you know what that is? That's C sub V delta T from 1 to 2. Well, we got T1 and T2. So we know what C sub V is for air. It's 0.717. And if you take T2 minus T1, that's what delta means. It means final minus initial. Delta in mathematics is always final minus initial. And so that's what you're going to get for your delta U. And then we're going from 1 to 2. Well, Q is 0. Look, Q is 0. And we're going to solve for a little w. All right, well, I'm going to do that. You do it. We'll see what we get for the little w there, for the delta U. I'm getting delta U is 471. 471.8. 471.8. I wonder if that's what I got when I did it before. Let me see. Yeah, that's what I got before. Now, we're going to solve for little w now. Look at here. if you know this, and you know this, and you have an equation, you should be able to get that. It looks to me like it's going to be either plus or minus 471.8. But which is it? Is the work positive or negative going from 1 to 2? What do you guys think?
Negative.
It's negative because it's compression. See, this is the compression stroke. This is the burn. This is the power stroke. This is the exhaust intake stroke. Okay, well, let's go from 2 to 3, shall we? Here we go. We're going to go from 2 to 3. We're doing from 2 to 3 now. Now, from 2 to 3, that's an isobar. Have I taught you guys that the heat transfer with an isobar is equal to the delta H? I've taught you that. And the delta H is equal to C sub P delta T. So we can get this Q here by going 1004 kilojoules per kilogram Kelvin times the change in temperature from 2 to 3. Well, what's that? 2400 minus 948. Okay. Now we can do that, and we can get the heat transfer per mass from 2 to 3 using this. Hey, there's Tyler and Mark. Welcome. For anybody that tuned in late, we're doing problem 1074. You've already worked on it. That's good. So I'm just going over it in minute detail and boring you to death. But I believe boredom is good. Okay, here goes. We're going to get the heat transfer per mass from 2 to 3. I'm doing it now. I got an answer. I'm getting the heat transfer per mass from 2 to 3 is 14. I think I'll round it off. No, I won't. I'll just keep the 8 there. 1457.8. I wonder if I did that before. Yeah, 14. Yeah, that's what I got before. How about that? We think this is 14.
I'm sorry, where did you get the 1.004 from?
Oh, thanks for asking. That's the C sub P for air.
Oh, okay.
Here, let me write them. C sub P for air is 1004
Okay.
kilojoules per kilogram Kelvin. And C sub V is 0.717 kilojoules per kilogram Kelvin. But thank you for asking.
Thank you.
Anytime. Hey, we're doing good now. Now let's get this delta U. Okay, we're going to go from 2 to 3. Let me write that down here. Delta U from 2 to 3. Now that's going to be C sub V times delta T from 2 to 3. Okay, well, we have the temperatures, the 2 and 3. Take the final minus the initial, multiply by the 0.717. Did you get 1041 kilojoules per kilogram? And I'm waiting for an
Yes, sir.
Hey, good. There's one. We think this is 1041. All right. Hey, now looky here. We have an equation, delta U, but now we're going from 2 to 3 this time. We're going from 2 to 3. Delta U from 2 to 3 is equal to heat transfer from 2 to 3 minus the work from 2 to 3. And look, we know the delta U, and we know that we should be able to solve and get the work from 2 to 3. Can you see it? We should be able to. The work from 2 to 3 is, I'm going to do it, you do it, let's see what we get. Well, I got an answer. The answer I got is 416.7. 416.7. Yeah, that's pretty close. Is it positive or negative going from 2 to 3, the work?
Positive.
Positive or negative work going from 2 to 3?
Positive.
It's positive. Let's check it and make sure it's right. There's another way to get that work. Let me make some room here. But I think we did it right. But see, there's another way to get the work from 2 to 3. You know that work is the area under your PV graph from 2 to 3. You all know that. Well, the pressure is 6,000, so you could pull it out. It's a constant. 6,000 kilopascals. And when you integrate the dV, you're just going to get the delta V from 2 to 3, aren't you? So I want you to take 6,000 kilopascals and multiply by the difference between V3 and V2. We have them up there. I'm going to do that. Here, I'll write it out for you. 6,000 kilopascals. V3 is 0.1148 minus 0.0453. And now those happen to be cubic meters per kilogram. All right, let's do that and let's get the work a different way. Okay, here goes. Well, I got an answer. I'm getting 417 kilojoules per kilogram. Now, what do we get doing it the other way? And well, that's pretty dang close, guys. We got 416.7. This way we got 417. I'm pretty happy with that. I am not going to stress out over that. But see, you can check some of this stuff. It's called checking your work. Not a bad idea. So let's move on. We're doing the diesel cycle, problem 1074. It's a diesel cycle. It has two adiabats. It's got two adiabats. One isobar and one isocore. That's what the diesel cycle is. Now we're going to figure out these delta U's. Here we go. Unless there's a comment or question. Well, I didn't hear any comments or questions, so we got a good group here. Tyler, Mark, Levi, Kristen, Coy, Kerman, Jackson, Daniel, Abdullah, Don. Good group. Okay, here goes. By the way, this equation right here has a name. See this delta U equals Q minus W? That has a name. And you all know the name of that equation, don't you?
Yes, sir.
Yeah, you know the name of that equation. It's one of the most important equations in our course. It's called the of
First law for control mass.
yeah, there you go. First law of thermodynamics for control mass. There you go. All right. Well, let's get this one here. Now, if you want delta U from 3 to 4, well, then you go 0.717 times delta T from 3 to 4. Let me do that and see what I get. Here it goes. Okay. Well, I got an answer, and I think it's negative. I'm getting an answer that's negative 900. I'll round it up, 950. Well, here we go, 957.9. There you go. How come it's negative? How come the change in, what do they call that? The internal energy. The change in specific internal energy is negative. How come it's negative?
There's an output of work.
That's a pretty good answer. I kind of like it. The answer I really wanted though is it's getting colder.
Cooler.
It's getting cooler, yeah. When you get cooler, you lose that internal energy. Go out in a snowstorm sometime. You'll lose some of your internal energy. You'll cool off. Okay, now let's do this one. Well, no, wait a minute. Oh, okay, let's do this one. What's the work going to be? You have this lovely equation here. If you know this and this, only we're doing from 3 to 4 now. If you go from 3 to 4, you should be able to get the work. It's either plus or minus 957.9.
It's positive.
And it's plus because when you go from 3 to 4, you're expanding. See, when expansion work is positive, compressive work is negative. Hey, I never put my other isotherm in there. Let me put my other isotherm in there. We have another isotherm at state 2, which is 948. Okay, here we go. Kind of squeeze it in there. This one here is the 948 Kelvin. So we got all our isotherms on there. And notice, notice the adiabats are steeper than the isotherms. Here, let me write that. I know I've told you this over and over again, but I believe in repetition. Adiabats are steeper than, I'm running out of room here, than are the isotherms. See, let's say you were in a little car and you were going up this hill, bum, 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 there you go, chugga, 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 puff, puff, they're going up the hill. Well, if you went up this hill, it's steeper. Look, it's steeper going up that hill because it's an adiabat. Adiabats are steeper than isotherm. Okay, good. Well, we're having fun. Let's figure out this delta U now here. Now this is delta U from 4 to 1. Same drill. It's just this time we're going to go from 4 to 1. All right, I'm going to do that. Here goes. Wonder if I did that right. I'm getting a negative 500. I think I'll round it off. I think I'll just round it off to 555. Negative. So you must have got colder going from 4 to 1. Yeah, you did. I can see that. That's colder. Yeah. Okay. Now how are we going to get the Q and the work? Hey, wait a minute. Isocores don't do any work, do they? Won't this work be 0 right here? See, that's an isocore from 4 to 1. They don't do any work. So that's 0. I'm getting too hot. I got to take this coat off. So we should be able to figure this heat transfer using our first law. Yeah, that feels better. Using the first law, this is either going to be plus or minus 555, but I wonder, what will it be from 4 to 1? You know what? I think it's minus. I think heat transfer is going. You're warming up Oklahoma is what you're doing. When that diesel truck goes by, that hot exhaust is warming up Oklahoma. And by Jove, I think we've got it. Yay. Now let's answer their questions and move on to the Stirling cycle. But first, before we answer their questions, is there any question on any little old thing?
No, sir.
Okay. Hopefully you're just bored out of your gourd. Now they wanted some stuff. Let me make some room here. Let me see what they wanted. Let me get my book here and I'll read you what they wanted. They wanted the compression ratio, thermal efficiency. Well, let's do the compression ratio. Now, the compression ratio they have a little symbol R for it. They might have a little C here. I don't know. I don't remember. But all it is it's this V1 here divided by V2. That's all it is. V1 is 0.8761. Right? No. Yeah, that's right. And V2 is 0.0453. Okay, here goes. We're going to get the compression ratio. 0.8761 divided by 0.0453. Holy cow, it's 19.3. Diesel cycles have a pretty big compression ratio. See, they don't need spark plugs because they get so dang hot when that compression gets so hot. They have this glow plug and it explodes. It sparks and explodes the diesel. They don't have to have a spark plug because they have a very big compression ratio. Now they also have a thing called a cutoff ratio. And what that is, that's your V3 over V2. So what that is 0.1148, right? Divided by 0.0453. I don't really know what they use the cutoff ratio for. I don't design diesel engines, but I'm sure it has a use. And I'm getting 2.53 for the cutoff ratio. Now they also ask for the efficiency. Well, let me add these up and get the net work. See, this is going to be the net work per mass. And this here, when you add it up, when you add these up, you get the net heat transfer per mass. For a cycle, they have to be equal. So I'm going to add these up and see if I get equal. Let me see, 1457.8 minus 555. I'm getting 902.8 for this one. Now I'm going to add these up. 471.8 negative. 416.7. 957.9. I'm getting 902.8. Came out the same because it's a cycle. And for a cycle, if you add up all the heat transfers per mass, for a cycle, it has to equal adding up all the work per mass in the cycle. So that's good. Now we're going to get the thermal efficiency. Here goes. Let me make some room right here. Symbol they use for that is a Greek letter eta. And what it is the net work per mass divided by the, it'd be the Q23. See, this is always something you desire. And what you desire, if you have a diesel engine, is you desire the net work. But it costs you, and you have to divide by the cost. Now the cost is you got to go pay money for this diesel fuel that you're burning going from 2 to 3. That's the burn, remember? And so this is going to be 902.8 divided by 1041. 1041. See, that's what you have to pay for. 2 to 3, you got to buy that diesel fuel.
All right, didn't you put it that it's the Q from 2 to 3, but the 1041 is the U from 2 to 3, or am I just not able to read it
I
right?
am wrong. I am dead wrong, and you are right. Thank you so very much. This is what you have to pay for right here, Kristen. Kristen helped us out, and I had it wrong, but I think it's right now. Now let me do that. And 902.8 divided by 1457.8. I'm getting, let's just round it off to 62%. I wonder if that's what I got when I did this before. Let's see. By Jove, I got 0.619 when I did it before. Well, we're not going to have any problem with that. It's around 62%. So I think we answered all their questions, and I'm pretty happy. And now we're going to do a Stirling cycle. But the floor is open for your questions or comments. Well, I guess you guys are happy with that. Let's move on. We're going to talk about the Stirling cycle now. You know, I could use this same chart here if I just erase the numbers. Yeah, let's do that. Let me see if I can erase these numbers. And we'll do a Stirling cycle. Here we go. All right. Well, we'll erase this because we're going to have to make a new one. We'll say goodbye to that one. No, we don't need any of this. Don't need any of that stuff. Okay, we're going to do problem 1082. We're going to do 1082, but it doesn't use air, it uses helium. But that doesn't scare us. It won't hurt us to use helium. But I tell you what, let's do. Let's look up the numbers for helium, shall we? Go to the back of your book and help me shop around for helium. And now what we're going to do now, we're not going to do 1074, we're going to do 1082. It's a Stirling cycle. (1082). All right. And it's a Stirling cycle. Go to the back and look up helium for me. And it says helium. Keep looking. All right, I'm getting close here. Helium. We're going to deal with helium this time. And that's the fuel for the sun. Did you know that? Well, actually, I think hydrogen is the fuel for the sun. You get, I believe it's 4 hydrogen molecules combined make a helium, give off a lot of energy. Okay, but R is equal to 2.0771. I'm looking this up in the back of the book. Kilojoules per kilogram Kelvin. And C sub P is, let me write this stuff down. C sub P is 5.193. kilojoules per kilogram Kelvin. And C sub V is 3.116. 3.116. And K, which is the specific heat ratio, you could divide those, but they've done it for us. It's 1.667. Actually, it's 1.66, a whole bunch of sixes, but we won't fight over that. So we looked up some stuff for helium. Now you need to know what a Stirling cycle is. A Stirling cycle is two isotherms. Let's draw it. Oh, gee. Come on, I can do better than that. It's got two isotherms. And let me get my red pencil here. There you go. And you know how isotherms go. They kind of go like this. I'm trying to make those dark enough to where you can see it's actually red. They're supposed to be red. And a Stirling cycle has two isotherms and two isocores. So it does this. It goes up this isotherm from 1 to 2. Then it goes straight up from 2 to 3. And then it comes straight down from 3 to 4. And then it goes straight down back to 1. Now you have a heat transfer in here from 2 to 3 and a heat transfer out here from 4 to 1, but you also have a heat transfer in here. You have 4 heat transfers from 3 to 4 and a heat transfer out from 1 to 2. Four heat transfers. But only 2 works. 2 of these little W's are 0. You see, going from 2 to 3 is an isocore, doesn't do any work. And 4 to 1 is an isocore, doesn't do any work. All right, now let me read this and see what we know and what we don't know. We're doing problem 1082 now. I lost my page. There it is. An air standard Stirling uses helium. The isothermal compression goes from 100 kilopascals, 37 Celsius. Well, here, let me write that down. See, this is 37 degrees Celsius, and this pressure here, they said is 100 kilopascals. 100 kilopascals. Okay. To 600 kilopascals. So we're going to go up to here. Now this is state 2, and it's 600 kilopascals. Well, now let's put that on our property table. State 1 is 37. Now these are going to be degrees Celsius.
Do you want that in Kelvin?
Didn't they say Celsius?
Yeah, it says Celsius. Don't you need to convert it to Kelvin?
Yeah, I think that'd be a good idea. Let me do that. I like that idea. Now what I did wasn't wrong. You don't get a thank you point because it wasn't wrong, but we're going to convert it to Kelvin because I think that's a good idea. I'm going to give you a virtual thank you point. There you go. What's 273 plus 37 roughly? 310. Did I do good?
Yes, sir.
Okay, I'm going to go 310 at state 1. I like Kelvin better. That's much nicer. Excellent. And the pressure at 1 is 100 kilopascal. Now we can get the V. We're going to do that together. P1V1 is equal to RT1. It's just that R now is over here. Did you ever notice that R, C sub P, C sub V, they all have the same units? They're very much related. They're like a little family. It goes like this. I think I've shown you this. If you subtract these two, you'll get R. If you don't believe me, subtract them and see what you get. Okay, we're doing the ideal gas law with helium, and R is 20771. So go for it, and we're going to get the specific volume. Here goes. This isn't hard. It may be boring, but it's not hard. I got an answer. I got 6.439. 6.439. But I need an
Sir.
Yay, I heard one. I wonder if I did this before. Let me look and see here. I might have. We'll look and see. Yeah, we're doing great. Doing great. Okay. Let me keep reading now. And an expansion takes place at 1200 K, and there is no regenerator. I'll need to explain about regenerators in a little bit. Expansion takes place at 1200 K. What they're talking about, this isotherm here is 1200 K. This is the expansion. There is no expansion from 2 to 3. That's an isochore. There's no expansion. No expansion. That's a top dead center is what it really is. And then it expands because there's heat transfer in. And you got that's your power stroke. There is no exhaust intake because this is a closed system. There's nothing that goes into the piston and nothing that comes out. But you do have a heat transfer out on this isochore. Maybe I can explain how that works. Well, let me keep reading. This is a 1080. We're doing 1082, guys. We're doing problem 1082. It's a Stirling cycle. Let me just tell you some things about the Stirling cycle. It was invented around somewhere around 1830, 1840. It was before the Civil War. It was invented in England by a guy by the name of Stirling, which figures. And he created an engine that could pump water out of the coal mines. This was the age of steam, and they had steam engines that would pump the water out of the coal mines. But there was a problem with the steam engine. When steam expands, it creates enormous pressure, and occasionally they had governors that would try to release the steam, and release valves. But occasionally they might get stuck or broken and it would blow up and people would be killed. That was the downside of the steam engine. There's a steam locomotive that blew up over by Carthage, Missouri, because of the high pressure of the steam in the steam engine locomotive. And pieces of that engine flew, I would say for miles, but I might be exaggerating. But big chunks of that engine flew all over the place. But see, the Stirling engine, it doesn't blow up. And it had some advantages. It also had some disadvantages. One of the disadvantages was it gets plenty hot. 1200K is pretty hot. The pressure isn't so bad. We'll find that pressure at state 3 here in a little bit. It's not the pressure, but it gets hot, and the metals in those days, gosh, that was a long time ago. What, 1820 or 1830? The metals just couldn't take it. And so after so many months or years, the engine would fail due to the metals failing with the high temperature. So they would have to shut it down and rebuild it. So that was the downside on that. But there was competition between the steam engine and the Stirling engine. If they'd had the right metals in those days, the Stirling engine, in my opinion, would have taken over. And instead of the age of steam, it would have been the age of Stirling. But nowadays we have wonderful metals that can stand the heat, and the Stirling engine has come back into its own, and it has some advantages. I'll tell you about them later, but we got to get this done. And we're going to go from 1 to 2. And hey, look at here. 1 to 2 is an isotherm. So wouldn't that temperature at 2 be 310? And look at here. They told us that the temperature here is 1200. Well, that's the same temperature at 3 and 4. So the temperature is 1200 at 3 and 1200 at 4. Now here's something else. State 1, you've got, you know what the specific volume is, but that's the same specific volume at 4. So we know that's 6.439. Hey, looky here. P4V4 equals RT4. Let's do that. P4V4 is equal to RT4. We should be able to get the pressure at 4, shouldn't we? Okay. I'm going to do that. I want you to do it. I want you to get the pressure here at 4 for me. On your mark, get set, go. But now you can't use the air 0.287 anymore. You've got to use 2.0771. You have to use a helium. We're dealing with helium here. See what I'm doing is I'm plugging in V4 because we know what it is. I'm plugging in the constant for helium and T4, and I got the pressure at 4. I think it's 387. 387.1. I wonder if that's what I got. Let me see, 387.1.
I guess
I
so.
just have
I got that.
387. Yeah, I think we're doing great. Okay. What are we going to do at 2, though? Let me think about this. Going from 1 to 2.
Well, the problem statement says that it's state 2 at 600 kPa.
Oh, thank
So-
you so very much. Good going. I forgot all about that. State 2 is 600. So, beautiful. Look here. This is easy, isn't it? P2V2. I'm glad Kristen spoke up. I would have been staring at this thing for another 10 minutes. But I think we know P2. It was given. And we know R and we know T2. Yeah, okay, let's get V2. Here goes. But you have to use the R for helium. Well, I got an answer. I'm getting 1.073. Let's see if that's what I got when I did it before. 1.073. Yeah. Yep. 1.07. Oh, 1.0732 if you want to be really nitpicky about it. Yeah. Great. All right. Well, now how are we going to get state 3? Now, let me think here.
It's an isocore, so
It's an
then-
isocore. Good thinking. So 2 and 3 have to have the same specific volume, don't they? Yeah, look at here. This is going to be 1.0732, just like 2 is. They're the same. 2 and 3 are the same. Hey, now look. P3V3 equals RT3. And we know T3, we know R, and we know V3. Let's get P3. Here goes. Now what's the R? It's 2.0771. T3 is 1200 divided by 1.0732. Da-da, I'm getting 2322.5. Now, how about you? Wonder if that's what I got. 2, 3. I think I rounded it off to 2, 3, 2, 3, but we won't fight over it. We're doing great. Okay, now let's get these delta U's. Okay, delta U's, how do you do that? Well, same way we've been doing it. Do you remember how we did it? Got those delta U's before?
Before we were using CU delta T. But
Yeah,
wasn't that before
yeah,
for 2 to 3 and 4 to 1?
That's what we did. We went delta U from 1 to 2 is C sub V delta T from 1 to 2. That'll work. Well, wait a minute. Auga. There is no change in temperature from 1 to 2. So you know what? I think delta U is 0 from 1 to 2. What do you think? It's an ideal gas. Specific internal energy depends only on the temperature. If you have an isotherm, Your internal energy doesn't change. Hey, we got 2 zeros there. See there? From 3 to 4 is a constant temperature. There's no change in internal energy. Tell you what, though, let's go from 2 to 3. I think we can get something from 2 to 3 now. Did y'all, little Southern talk, y'all understand how come those two are zeros?
Yes, sir.
Hey, good deal. Okay, we're going to do this one now. Now watch it, this C sub V, that's not 0.717 anymore. This is not air. Hey, we got some more customers here. Tyler, Ross, Mark. Yeah, some of them have been around. Jackson, Abdullah, Daniel, Don. Okay, we need, oops, almost got that erased. We need 3.116 kilojoules per kilogram Kelvin times the change in temperature from 2 to 3. Could almost do that in my head, but I better not risk it. It's 1200 minus 310. Okay, here goes. We're going to get delta U from 2 to 3. Here goes 1200 minus 310 times 3.116. Did you get 2773? I wonder if I rounded off. Let me see. I just call it 2773. That's close enough. Now going from 4 to 1, I could write it out for you, but I think it's going to be a minus 2773. Because it's the same two temperatures, it's just that you're getting colder. Let's get these boxes here now. On your final exam, these are going to be worth a point apiece. So every box you get right is worth a point. That'll be good. Looky here. First law, delta U is equal to Q minus little w. If you know delta U and you know little w, you should be able to get the heat transfer from 2 to 3. I think it's 2773, don't you?
Yes, sir.
I think so. Because when you subtract 0, you get, yeah, that'll work. Now, what about this here? Using the same thing going from 4 to 1. We know the work, we know the delta U. Wouldn't that be a minus 2773 for the heat transfer from 4 to 1?
Yes, sir.
Yeah. Now let me tell you something that the guy that invented this engine, he was plenty smart. He took this heat here and instead of heating up, well, he was in England at the time. Instead of just making the countryside a little warmer, he was able to capture some of this heat, or most of it, in a thing called a regenerator. They call this a regenerator. Now the problem we're working, this problem 1082, if you'll read it, it says there is no regenerator. So that heat there is not being captured for this problem here, but I'm just telling you, uh-oh, I don't like that. My computer said something, I don't have enough free space on my OneDrive. What the heck is a OneDrive? That's scary.
Online cloud through Microsoft. It may be trying to save it or save your recording to it.
Oh. Ooh. Well, I want to save my recording, doggone it. because somebody might have missed this lecture and they might need it to study for their final. I just bought this computer yesterday.
Yeah, OneDrive is
It's a
OneDrive's
hit.
cloud-based. It's all internet-based.
Oh,
So it wouldn't.
it's not my computer. It's something else.
Yeah, it'll probably continue to record it to your computer. It just most likely won't base it in the cloud or
Oh,
like
good.
copy it in the cloud.
Good. That
essentially.
makes me feel better. Now
That's
let's
all.
see. Where were we? I got lost here. Oh, I was telling you about regenerators. Now this problem doesn't have one, but Mr. Sterling, here's what he did. He was able to save all or most of this Q41, which we just figured out is 2,773 kilojoules per kilogram. That would have just heated up the English countryside. And he was able to return that back in here. And he didn't have to pay for that heat. Isn't that nice? Now he still had to pay for this heat transfer here. That cost him money. You got to burn some kind of fuel to run this engine, like all engines, like a diesel engine runs on diesel. And these, I forget what they use. Probably they could use coal. They could get coal hot enough to run it.
I've seen
But
people
isn't that
build them
neat?
and use
You
candles.
save some money that way. I'll tell you what's in here. It's like a bunch of real fine steel wool. Very, very fine steel wool in this box here. And you make it hotter and colder, up to 100 times a second. See, this engine has it's revolving. It's spinning. Maybe a 100, well, what would that be? 6,000 RPM? Let's say it's got 6,000 RPM. Well, would that be 100 times a second? I don't know. Let's see. 6,000 RPM. That's revolutions per minute. 6,000 RPM. And then if you multiply by a minute over 60 seconds, yeah, you'll get 100 revolutions per second. Well, what I'm telling you is that the steel wool in here, if it's very fine, can heat up and cool off 100 times a second. If it's real fine, it's amazing. Not only can fine metal shavings do that, but air can do that. Air can heat up and cool off 100 times a second. And that's what's happening. You're going from 37 degrees Celsius, which is 210 Kelvin, to 1200 Kelvin, 100 times a second. Can you believe that? That air could heat up, cool off 100 times a second? Well, it's doing it. Very clever. Only this particular engine doesn't have a regenerator. Disconnect the regenerator. You're going to have to pay for both of these heat inputs. So we haven't got those figured out yet. We got 4 more boxes to do, and we're running out of time, but we got time to do those 4 boxes. And I'm going to give you a homework. Did I ever give you a homework problem?
No, never this week.
Oh, I tell you,
Wait,
I tell you what I could do for the homework problem. You finish that. You got 4 more boxes for your homework. You finish it. You got 4 more boxes to fill in. Let me give you a little teeny tiny hint that might help you. And then on Wednesday, if you need me to post that, I'll be glad to. But here's your homework. Finish the 1082. Now there's a couple of other things you're supposed to do. I think you're supposed to find the probably the efficiency. Now let me read it. Let me see what it says here. 1082, okay. Yeah, they want you to find the work and heat transfer on all four processes. Yeah, yeah, yeah. The thermal cycle efficiency. Yeah, yeah, yeah. You're going to find these four missing things. You're going to finish problem 1082, and you're going to find the thermal efficiency. And I'll talk to you a little bit about it on, what is today, Tuesday? On Thursday. On Thursday, I'll talk to you about it. And don't turn it in. This is the love of knowledge for its own sake. But I want you to finish those. But let me give you a little hint that'll help you. We have an equation for an ideal gas isotherm that goes like this. I don't know if you remember it. Do you remember that equation for an ideal gas isotherm?
Yes, sir.
See, it's really a polytropic process with n equals to 1. And so you can get the work from 1 to 2 and from 3 to 4, because I think you know everything. You know all the V's and the P's and the V's, and you got your first law, so I know you can finish that, and you can start studying for your final.
This
And
may
we'll
be a
talk
dumb
about it.
question, sir.
Go ahead, I'm listening. Question.
In the last process, or in the last engine that we were working on, the last cycle,
The diesel.
you would use the integral of PDV, so
Yes.
pressure and delta V.
That's
Would
right.
that not be something we could use on this particular cycle?
Excellent question. Now let me think. I'll stall while I have a sip of water here. I'm stalling. Okay. What my wonderful student is asking, I think it was Don. Is that Don?
Yes, sir.
I think what he's asking is the area, we have an equation that goes like this. Is the area underneath this graph, namely, let's look at this area here. Here, we'll shade it in. Is that area equal to little w 3, 4? And the answer is, yeah, I think it is. I think the area it's equal to the area under that graph. But I also think it's equal to this. I think this is equal to that. Don?
I'll run it real quick and make sure.
Yeah.
Just for verification.
Yeah, run it real quick and see if it doesn't work. I think it does. I like that question. Next. Okay, well here's your assignment. Study for your final. Finish this, finish these here, find the net work and the net heat transfer. See, these cancel, but when you calculate your thermal or your efficiency, you got to pay for that. It's not free because we don't have a regenerator. All right, anything else? I'm putting this over the little red end button here, and when I push that, it's over for today.
See you in the morning.
Hey, I'll see you in the morning.
Professor,
Yes.
when are you thinking that you're going to have the homework and quiz grades up?
I need to do that muy pronto is what I need to do. I need to do that muy pronto.
Would agree.
Like now for the final exam, is it
Yeah.
about the same length as the other exams?
Yeah.
Or is it
no.
longer? Or
Same length.
okay. All right.
But you have, I think, 3 days to do it in.
Yeah, I know, but I have 4 to do with you in those 3 days. So,
Yeah,
you know.
I feel a little bit sorry for you.
Yeah,
But
I mean, you could go ahead and give me an extra day so that way I can do one each day. No?
You'll be fine. I have
All
no
right.
doubt. You'll be
See
fine.
you tomorrow.
Okay,
Is there a set day for the final, sir?
I'm going to post them Sunday night.
Thank you, sir.
Yep. Okay, guys. Bye-bye to all.
Bye.
Thank you, sir.
Thank
Thanks, sir.
you.